Good.
Right, so we are live on Facebook. Hello, everyone. Thank you for joining us today at another exciting session by the Oxford University Quantum Information Society. I am Hamza Wasim, the events officer of Quantum Information Society. And today our distinguished speaker is Professor Carlo Rovelli. Carlo is one of the founders of Loop Quantum Gravity. He is also interested in the philosophy of quantum mechanics and the philosophy of science generally. And he has written some popular books which have been translated in multiple languages. Some books that I can name off the top of my head include 7 Brief Lessons on Physics, The Order of Time, and most recently, Helgoland. In this session, Carlo will be talking about an interpretation of quantum mechanics, which he introduced in the 1990s. Formally, this is called the relational interpretation of quantum mechanics. And Carlo will be speaking about the role of relations and information in making sense of quantum theory. Over to you, Carlo.
Thank you very much. Thank you, everybody, for listening. It's a pleasure, and I'm thrilled to talk about quantum mechanics and trying to make sense of quantum mechanics in the hiding place, Oxford, which is a hiding place of the many world interpretation people presenting an alternative to many worlds, so a different possibility of looking at quantum mechanics. So let me start share my screen. Here we are. If there's anything wrong, let me know that there's anything wrong. Otherwise, assume everything is fine. So,
it's all right. Yeah.
Great, thank you. So that's the title, Making Sense of the Quantum, the Relational Interpretation. And the plan of what I'm going to do is to start by saying what the problem is. Because, of course, you might study quantum mechanics and use quantum mechanics without thinking about this problem. That's nothing wrong with that. It's legitimate and it's good, but nevertheless, there is a beautiful problem there to be discussed. I say, what is the problem of quantum mechanics? Then, before introducing the actual relational interpretation, I'll make a historical consideration about the birth of quantum mechanics, which I think is useful to pinpoint where I think is the crucial point and a possible misunderstanding of the formalism which is around. Then I'll discuss about what is relational quantum mechanics, what's the main idea. That will be short, will be just a few key points, and that will be the center of the talk. And I'll compare this with other possible views of quantum mechanics. I will take some time about talk about information, because many of you guys are interested in quantum information, the notion of quantum information. And when the relational interpretation was born in the 90s, that was before a lot of quantum informational talks. It was formulated in terms of information. So it was I think information is it's a wonderful notion for describing, for dealing with quantum mechanics, and I'll try to explain why, in which sense. And I will. One of the games that started in the 90s, it's writing postulates in informational terms for quantum theory, and I will say what they are and how. What the role they play in reading quantum mechanics. And then somehow I'll close with preaching a little bit about what is the wave function, because I think a simple manner ways of viewing the problem interpretation of quantum mechanics is asking what is really the wave function. Is it the stuff which is out there? Is it something in our mind? Is it it's a calculation device? And I will challenge some of the ideas that I repeat are dominant in Oxford. So let me start from what is a problem. Just as a slide, only just an introduction. You all know that quantum theory is perhaps the best physical theory we ever had, in the sense that so far has never gone wrong, which doesn't mean it will always go right, but so far it's has never gone wrong. And more than that, we have no idea about its limits. I mean, we have limits about specific dynamical theories like general relativity. It's classical. We don't know a quantum version. We think the standard model goes wrong at high energy. We have reasons for say that, but we have no direct indication that quantum mechanics goes wrong at all. So for the moment, it's the best theory we have, and of course, it has predicted spectacular things. You know, quantum computers, lasers, all sort of stuff that we use in our technology. But in spite of this, wow, how good it is, it remained mysterious. Why it remained mysterious? In a slide, in a single slide, for this reason, because the way it's formulated in textbook, the way you learn it, there's a quantum system there, and the theory doesn't really tell you in a coherent and comprehensible and simple way what happens in the system. It only tells you the result of a measurement, namely what happened when you look at it, the way the system interacts with you, the way it affects you, and it gives probability amplitudes. If you see this, then there's a certain probability of seeing something else. The calculation device, I mean, the interpreted part of the mathematical device is this probability given some observation, some other observations, which value can it have, and what are the probability distributions over the values. But this is a funny way of presenting physics, right? In fact, from the very beginning, how does nature care whether we're observing or not? I mean, what is going on if nobody is observing in between one observation and the other? And roughly, this is a list of the this is a simplified list of the ways people think about that, the way people, the possible ways of thinking about that. It's not an exhaustive list. Each one of these alternatives comes with variations. But I would say that 90% of views of quantum mechanics can be put together in this group of alternatives. The first one, the first line here, I've called it the Copenhagen view. It's very vague, or the laboratory view. And I would say that the majority of physicists hold this view. By physicists, I mean physicists, including condensed matter physicists, atmospheric physicists, matter theory, astrophysicists, and so on. And the way of viewing the theory here is that you have quantum systems. This little picture here is a quantum system. And then you have the macroscopic world, which is classical. You yourself are classical, your apparatus is classical, your telescope is classical, your laboratory thing is classical. And what you're actually describing is how the quantum system affect the macroscopic world. So if you think of the particle, and then the particle is in a certain position when it hits the screen, essentially. So this is legitimate. The question is, well, we know that the macroscopic objects are themselves quantum mechanical. So when is it that is there a boundary? Does quantum mechanics stops to hold at some point? Well, we know it doesn't, because we can consider pieces of apparatus quantum mechanically, ultimately the prediction the same. So that's a good way of viewing quantum mechanics if you don't ask too many questions, like the quantum properties of the macroscopic world itself, that should be there. They are perhaps difficult to see, but should be there. Or what happens in the system when it's not interacting with something macroscopic. So imagine that you are in an early universe where everything is quantum, nothing macroscopic is yes come out. How do you describe a universe? You cannot in this logic. An extreme version of the same logic, which is popular among some philosophers, it's called cubism, has been sort of the dot on the i's have been put in recently, which sort of take the so-called Heisenberg cut, the separation between the macroscopic world and the quantum world, all the way back. Think, oh, okay, everything is quantum, but at the end of the story, there is some knowledge, some agent that has some knowledge, and that's what quantum mechanics is about. Quantum mechanics is about some subject that has knowledge, knows something about the world, and it only knows something about the world when something interacts with it. Itself, himself, herself, okay? And on the basis of this, it can predict future interaction and so on. So it's a very sort of extremely instrumentalist position in which we don't say anything about the world itself. They only say what happens when I interact with the world. I'll skip relational quantum mechanics, which is what I'm going to talk about, and then I'll go back to an alternative group of interpretations. One is many world, popular in Oxford. Both in the philosophy department, both philosophers. Here you heard my good friend Simon Saunders, who's a defender of that, or previous Oxford philosophers like David Wallace, who's now in Pittsburgh, but also also some physicists there are in that direction, and it's part of a group of manners of wave quantum mechanics, which makes the quantum state, or I would say the wave function, I'll use the two expressions interchangeably, one with the other, as the main thing. So there is a wave function, and that's it. And there's an Hamiltonian that evolves the wave function, and from there, you're supposed to reconstruct what you observe. You're supposed to take out probabilities. You have a long story to build to do that. A different possibility is to also say that there is a big wave function, but beside the wave function, that's not the only thing to do, and you shouldn't extract anything from that. There is also the actual world. So there is a wave and also the particle. There is the big wave function of the macroscopic apparatus, but there's also the macroscopic apparatus in some particular position. So you have everything, and you have equations, the Schrodinger equation for the wave, but equations for the actual variable, which are guided by the wave. And this is the hidden variables, main hidden variable series, like de Broglie-Bohm or pilot wave theory. They're formulated in this manner. So once again, here there's no probability, no fundamental probability. In many worlds, there's no fundamental probability in hidden variables. And finally, I've put at the end, there are also these people in Oxford, Roger Penrose, another good friend with whom I disagree on these things, who basically say the only way to make sense of quantum mechanics is to think that it's wrong. It's right within a certain approximation, but to make something coherent, it has to be wrong more generally. The Schrodinger equation and its linearity must be wrong. So what really happened is that the wave function, most physical collapse interpretations are based on a modification of the unit evolution of the wave function. The wave function actually doesn't always follow the Schrodinger equation. When there is something macroscopic, something else behave, which accounts, and again, story will given, which accounts for what we see specifically. Now, again, this is, each one comes from various versions, and there are, cross positions, but roughly these are the alternative, and I'll use the comparison between the different alternatives down the line. Before going ahead, how should we think about the fact that all these possibilities? One way of thinking is that, well, one is right and one is wrong, and we have to fight one another until one kills all the others. Who is right? The Christians or the Muslims? Let's fight, make a war, and see who wins. But perhaps there's a better way of thinking about that, and Richard Feynman has a remarkable way of talking about this, which I like a lot, and I want to quote him to express what is my way of thinking about these things. Feynman says, let me quote him literally, one of the amazing characteristics of nature is the variety of interpretation schemes it admits. And I think here in this situation, I've spent a lot of time studying all these interpretations, and to my disappointment, they're actually coherent, all of them. I tried hard to show how incoherent are the ones I don't like, but they are not incoherent, they are coherent. So it's true that nature can be interpreted in these different manners. All right, so Feynman says what to do in that situation, and he has this fantastic line, says every theoretical physicist who is any good. Now, I don't know what Feynman means by any good theoretical physics, but whatever. So any good theoretical physics knows 6 or 7 different theoretical representations for exactly the same physics. Wow. Here he seems to be saying, oh, come on, they're all good. they're all the same. No, 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 they're not. They say they're all coherent, they're all good. And you better know all of them, because that's how you better understand nature. And we must keep all of them in our head, because one of them might turn out to be the fruitful one. And I think that this is right on the point. Apart from the physical collapse, they're empirically indistinguishable, these various interpretations. So if you want to be a philosopher and say, well, they're empirically indistinguishable, so what's the point? I mean, it's just empty blah, blah, blah. I mean, empirically, we cannot make experiment to distinguish that. You're right, strictly speaking, but you're wrong, scientifically speaking. And let me make an analogy. Is the Earth the center of the universe? Well, if you think for a moment, this is an empirically unsolvable question. There's no way to measure the center of the universe. It's just an interpretation. I mean, you can interpret the movement of the planet, put in the center whatever you want. And if you study relativity, general relativity, even more, I mean, you just put the center whatever you want. So are we saying something meaningful when we say that the Earth is not the center of the universe? Well, strictly speaking, no, because it's meaningless. But scientifically speaking, yes, because it frames your way of thinking about motion in a way that allows the development of Huygens, Newtonian mechanics, Galileo, and all the rest. So it's a right interpretation. It's a fruitful interpretation. And among these various ways of viewing quantum mechanics, I'm not going through this slide exactly line by line, but I want to point out that each one of them has some clear advantages, which is the reason people are in love with them. Some clear conceptual cost. You have to pay a price to believe any of this, okay? Not to ask some questions, to believe that there are many walls, to believe there are principal hidden variables which you cannot see, but they're there, like ghosts, and so on. To believe something which we haven't observed there. So there's always a cost, which is a reason for which other people don't like that particular interpretation. And each one has a sort of philosophical coloring. I think that they're all defendable, but if we discuss long enough, if we use them for doing theory, I'm doing quantum gravity, I need an interpretation to think about quantum gravity, then slowly there will be some coming agreement. Let me sharpen on where the problem is a little bit by telling you what each interpretation says about the simplest quantum mechanical phenomenon. First one, Marie Curie, radioactivity, right? You have an atom, a nucleus of an atom or molecule or whatever, uranium, and then it splits out something, a particle. It breaks up or an alpha particle or a beta particle, an electron. So what happens is that at some time you have the atom and say you have some detector, some Geiger detector around, and some later time we see one detector to click. That's what we see, okay? And the way, so the simplest thing is, well, okay, there's a particle coming out from here and zipping to that one. But actually that's not what our mathematics says. Our mathematics doesn't say that there's a particle coming out from here and zipping there. If you use quantum mechanics, what you say is that there is a wave function, right, which spreads, it goes out slowly from the, look how beautiful this picture I've been able to do. It moves out symmetrically out of the, slowly leaks out from the, from the nucleus, the tunnel effect. So then the Schrodinger equation spread it around until one of the detector clicks, and which one is given by and the time at which clicks is given by a probability calculation out of the wave, and then you have the waves that suddenly rearrange itself. That's what we do in our calculation, and now it happens to be at that thing. And of course, you all know another way of saying the same thing, which is the way Schrodinger put it, came from a conversation with Einstein, in fact, in which, again, you have a system that can evolve in two ways, like the electron, the radiative particle can go in various directions, and suppose you can, there's a variable x that's distinguished, it can go to A and B, and suppose you have a cat, and the cat observes whether it's A and B and sees that A is realized. So this detector clicks. But then what if I think that the cat itself is a quantum system? And so I describe the same thing from the perspective of an observer which is outside. And so there are two possibilities, like the electron, the wave of the electron being here and here. So there would be a wave. Here is a state psi, which is a linear combination of this, a quantum superposition of these two. So this means that the cat is a quantum superposition of two states. And in my calculation, when I see it, the cat is in a superposition of two states. So is the variable x that distinguishes these two at this time, before I look at it, has the value a or not? It has value a for the cat, not for me. So what's going on here? What are the possible solutions? And very briefly, the various solutions are cubism, which is forget about the cat. The only thing, forget about the state of the cat. The only thing you can talk about is fix an agent, and everything else is not something that your sprite is supposed to describe where it is. The only thing you can describe is the actual observation that the agent does. Many worlds, my good friend Simon Sanders that came to talk to you last week or 2 weeks ago, I don't know. His solution in the many world is that there is just a wave. So in the wave, there are both position of the system. The cat is always asleep and also awake or dead or alive, depending how you want to play this game. And so why do you see only one cat? Well, because there are also two of you, right? Because you're also described by a wave. So the actual big wave function includes a version of you after you have interacted with the cat that sees the cat in one state and another version of you that sees the cat in the other state, which to believe that, you have to believe that there are two copies of you every time there's a quantum phenomenon. And since quantum phenomena, there are plenty continuously, there are many copies of you. So they're actually equal real as yourself, many versions of yourself with respect to which the world has all possible different configuration and state. So yes, you can make sense of quantum mechanics with the many world at the point, at the price of getting convinced. And since this is empirically indemonstrable, but nevertheless is useful for thinking, you have to believe that in the world, you are just one of the copy of many sort of friends or cyber copies of yourself. Each one of these has a little sees a little different worlds, and not just two, but zillions of copies of yourself. We really have to go that way. In the hidden variable, Debord, pilot weight, whatever, it's a similar story. There is also this way, so copies of you, but there is an extra variable which says which one of the various branches, that's the language, is actually filled with the real cat, the real atom and the real you, and which one is the other one. This sounds more reasonable. You have to come with all this extra baggage. You have to have all these extra variables, which are in principle invisible, right? So you justify the undeterminacy, uncertainty, which is in quantum mechanics, by adding ontology. Of course, quantum mechanics gives only probability, but you can always transform probabilities into ignorance probability by assuming that just the rest exists. What is not realized exists. And the physical collapse theory, it just says that the story is wrong. You don't know the two branches because you don't see interference. You need the two branches because the man outside can actually measure something which in the calculation would be wrong if the cat is alive or the cat is dead, but it's actually true if there's a quantum superposition. So the physical collapse, as soon as there is something big like the cat, the wave function changes, and you don't see interference. So that's why it would be empirically distinguishable. Oops. Good. So let me move toward the relational alternative, which I haven't talked so far, by going back in history for a moment. And the key point I want to stress is remind you that quantum mechanics was born twice, in 25 and in 26, so to say, after, of course, a long discussion and called old quantum mechanics, Bohr, and so on. Both Sommerfeld and so on. But the actual theory we call quantum mechanics was one quite independently along two different ways of thinking. One earlier. Mostly, I've been rereading all this paper. I think that Max Born is a little bit misappreciation, not sufficiently appreciated in this game. But it was Heisenberg that in 25 wrote a spectacular paper that sort of changed the game completely, introduced the idea of just looking at observables, introduced non-commutative variables. He didn't know that there were non-commutative variables, but and in a few years, a version of the theory was in a few months, a version of the theory was put on together, in which, that's a key point, there are variables that take a value A at some time t, another variable takes a value B at some time t prime, and you have probabilities of A given B and the formulas for that, which are computed using the same equations of classical theory, plus one, which is this one, xp minus bx is I h bar, which you know, all right? So you just have to have the mathematics in which this is realized in their version with the matrices, in Dirac version, just non-commutative variables. But you have all the variables of the classical theory, right? The equation of motion of the classical theory, plus this non-commutativity, and this, you compute probability amplitudes of variables given other variables. Now, there's no wave here. There's no quantum state here. They're just variables. And then, of course, a year later, Schrodinger came out with this idea of a wave, a function of x and t for one particle, a more general wave that satisfies differential equations. And at the beginning, he was hoping that this would work like Maxwell equations, but it doesn't. And the way you have to think about it is that, again, it gives probabilities. So again, you get probabilities, but through this intermediate thing, which is a wave. Let me go back to these guys, because I want to focus on the way these guys looked quantum theory. And let me go a little bit of historical details. This is a famous paper by Heisenberg, 25. It starts with pure philosophy. It says, I want to do a version of mechanics where it's just think that I observe and I don't ask about what I don't observe. He did that in an island which is Helgoland. You mentioned my book, my last book, Helgoland. The title of the book comes from the island where quantum mechanics was invented. It's a beautiful story. I mean, he was 23 alone there, and he talks a moment in which his calculations start to work. It's really exciting to reconstruct that days. It was June 7, 25. In his mind, there was all the problem with Niels Bohr. This is Niels Bohr about the atoms. So he had a long conversation with Niels Bohr about philosophy else. It was philosophy, and in particular, he was under the strong philosophical influence of Ernst Mach and his phenomenalism. And poetry. He was reading poets, Goethe. He was learning by heart a collection of poetry in which Goethe chants his love for Islam and for non-European ways of viewing the world. So it's a very wide angle set of influences on his mind. He writes this paper, he goes back very rapidly. Born and Jordan write this other paper in which there is just all the basis of quantum mechanics. There are the matrices, the PQ minus QP, equation, they refer to Heisenberg, and there is a notion of probability. Okay, somehow, for some funny, strange historical reason, Born got the Nobel Prize as the one who understood the quantum mechanics and probability, but everybody quotes a much later work of him after Schrodinger. But he had clear that these were about probabilities in 25. Okay, and then this is again the paper, the first paper by Heisenberg. This paper, look at the copy here. What do you think about that? Okay, this was in the UK, and this is Fleur giving to a young kid named Dirac, the first paper by Heisenberg, and Dirac independently come out from the same theory as those guys here, which is quantum mechanics. So this group of people completed the formulation of quantum mechanics, and Pauli, good friend of Heisenberg, So initially he refused to collaborate with the others, but then he jumps in and he computes the full spectrum of the hydrogen atom before Schrodinger in 25. Okay, so their theory, as again, the mathematics is the same equation of classical mechanics +1. The physics is that the values of these variables take are observations, and it's called contextuality. That's the key point, the point that gives rise to the discussion about the interpretation. And because they form a non-commutative algebra, they have a spectrum for the prediction of the theory that you can only, the value that they take are in the spectrum, and the probability are given by a certain formula. Now, the question is, so forget the wave function totally and use this way of thinking. What is this observation? And here is the key point. And now I go to relational quantum mechanics. And I have a slide in which I introduce the basic idea, once again referring to history and to the way Niels Bohr, I think, zooms in exactly in the discovery about nature, which is quantum, quantum theory. This is Niels Bohr. And careful, because this is half right, half wrong. Or I would say it's completely right, but it's misleading. And that's a step toward the relational interpretation. Niels Bohr says, look, this is what is the discovery of quantum mechanics. In classical physics, the interaction between an object, an atom, and the measuring apparatus can be overlooked. But in quantum physics, the interaction is an inseparable part of the phenomenon. The interaction is an inseparable part of the phenomenon. The unambiguous description of quantum phenomenon is, therefore, required in principle to include a description of the relevant aspect of the experimental arrangement. Now, this is exactly right, but it's completely misleading because it talks about apparatus and experimental arrangement. Think that in the 40s or 30s, when Bohr was thinking right these kind of things, most of the quantum phenomena were in the lab, and still are now for a condensed matter physicist. But the sun is quantum mechanically, I am quantum mechanically. Structure formulation in the universe now it's described using quantum mechanics, which works fantastically well. We reconstruct the shape of the CMB using quantum mechanics. There are no apparatuses there. There's no experimental arrangement there. So we have to rewrite the same phrase by Bohr by taking away the apparatus and the experimental arrangement and just rewrite it correctly. In classical physics, the properties of the object are determined respectively from interaction with whatever is around. Quantum physics is the discovery that the interactions are an inseparable aspect of the properties. That's the key point, and I will insist on that. So the unambiguous description of an object requires the inclusion of the objects involved in the interactions in which the object manifests itself. So forget about observation, forget about observables, forget about physics, forget about apparatuses, and replace observation with interaction and observables with relations. And that's the key idea of quantum mechanics. And that allows one, let me zoom it back, to make the following fundamental step. The properties of a physical system should not be thought as describing how the system is. They should be thought at describing the way the system interacts with other systems, the way it affects other systems. That's a step. If you take this step, suddenly everything goes in order. And that's the relational interpretation of quantum mechanics. Why everything goes in order? Because these steps allows you to understand two things. First of all, that properties, by what they are, as said before, they only have values at interactions. So you might attribute a property outside interactions, but you don't have to, and sometimes it's contradictory. So when we talk about a variable x having a value a at time t, t has to be an interaction time, because a property it means how it's affecting something else. And more importantly, properties comes out in interaction and are relative to the interacting system. So when we say that a property system has an observable x as value a at time t, we really mean as a value a with respect to the system which the system is interacting. Okay, if you had this extra label, which is the only thing you need, everything goes in order, because now you have to realize that the probability transition of quantum mechanics really are function of labeled variables. So they have to interpret it as the probability of A with respect to S being so given B with respect to S. And if you use them, that everything makes sense. So what's the point? The point is that these ones, the probability of B with respect to S prime given A with respect to S, these should not be used. This is meaningless. This is the mistake. All right. So here is the quintessential case. If you want, the cat, famous cat, Schrodinger will be happy. When the cat sees the variable X having value A, okay, that's a variable realized with respect to the cat. It has no bearing on what has no direct bearing in what the another observer will see, in the sense it has no bearing on the value of the variables of the cat, the quantum system, with respect to a third system, right? So with respect to a third system, if you have to compute the probability distribution of what cats and atom affect the third system, the interaction between cats and atom and a third system, you should not use that that the variable X has a value with respect to the cat. So the atom is this position with respect to the cat, but is not this position with respect to the observer. And that's relational quantum mechanics. If you do that, everything it's consistent. You don't need many worlds. You don't need hidden variable. You don't need a special dynamics of dynamical collapse. But you can talk about the cat, the variable with respect to the cat, with respect to the man, with respect to the atom. You can talk about what happens in distant galaxies without any observer, without any agent, without any person doing calculation. You just talk about relative variables. So the point about relational quantum mechanics is to replace measurement with any interaction, replace observer with any system. The theory is not about how a system affects a macroscopic system. It's not about it affect a special agent. It's just about every system affect any other systems. And the variables describe these things. And when it seems to give contradictions, is because you're forgetting the variables are labeled, and you are mixing up things. So this is the same as slide as before, where I have replaced observations here with what the theory describes is relative values, which are realized in interactions. And this is a way of thinking of quantum theory that it's coherent, it's consistent, and it avoids many copies of yourself, hidden variables. It avoids the need of complicated reconstruction what probability is. Probability is fundamental here. The theory is about probability. Recently, there have been a number of works, sort of theorems in quantum information and experiments in the lab, which are formulated in this language. Again, it would be wrong to say that proves this point of view, because all point of view are coherent. You can reinterpret everything from any coherent interpretation of quantum mechanics you want. Everything in the lab is not going to choose between interpretations, strictly speaking, because they are equivalent, apart the physical collapse. But you can use this language to make sense of what happened in the lab. And this is an example here. The facts are relative to physical system. That's a recent beautiful experiment, which presented in the language experimental rejection of observer independence in the quantum system. So facts depend on the observer. This is a sort of a laboratory realization of the Wigner-French scenario, in which you have one observer observing the other observer. So it's a laboratory realization of the cat that I gave you, where the cat is actually treated as a quantum system. And you can show, there's a technical sense in which you can see that with respect to the cat, something is true, but the same thing is not true with respect to the external observer. Now, where did the thing go wrong according to this perspective? By confusing relational with subjective. Okay, subjective is a thing that depend on my mind. Relational is a thing that depend on two systems. Many people talk about quantum mechanics slips into, it's about our observation, it's about our mind, it's about consciousness. Even, Wigner was a tribute to say that maybe it's just consciousness that collapses the wave function. It's total nonsense. If I say, and this is a key point, that the moon has a velocity with respect to the Earth and the moon has a velocity with respect to the sun, every physicist understands exactly what I'm saying. Velocity is relative. There's no velocity unless you say with respect to what. But when I say velocity with respect to the sun, I don't mean that the sun has a consciousness, is an observer that make a measurement, or that the Earth is an observer. I don't mean that. If there are observers, there, whatever, but that's not what we're talking about. We're talking about the fact that velocity is a relational quantity by itself. So the velocity, it's only defined moon, sun, or moon, earth. So relational quantum mechanics is the idea that all physical variables are like velocity. They're all relational. So when I say spin up, I implicitly mean spin up with respect to another system, with respect to the Stern-Gerlach apparatus when the thing has gone up. And if I remember that, and I don't make the mistake of mixing predictions with respect to one system computed in terms of variables with respect to another system, there are no quantum mechanical contradiction. How am I going with time? Well, I should hurry because I've been talking for 40 minutes, but I want to talk about information and the wave function. So I'll be fast in that. I have not mentioned information, but when in the first papers about the relational interpretation, the language was complete information. Now, information is a super useful concept, and it allows us to talk about quantum mechanical, what's special about quantum mechanics in a coherent way. But which notion of information? Because information is a very ambiguous word that is used with a variety of meanings that goes from a strictly physical one to highly semantic one. Information because it tells me something substantial about something else. But there is a way of defining information. It's purely physical. It goes back, you can find it in the original information theory by Shannon, which is the notion of relative information or mutual information, which is when you have two variables which are correlated, just correlation. So suppose you have two variables that can be sort of up and down, but there is some physical constraints such this is impossible, only these two are possible, okay? Then you say there is mutual information, because if you know one, you know the other one. Okay, and formalized by saying this has two possibilities, 1 and 2, this has two possibilities. So in principle, there are 4. There is information if there's a constraint such the number of allowed configuration, 1 and 2, is less than the product 2 times 2 times 4. And information is defined as the, use log base 2 and use bits as units as the log of the total of the number of states of one system plus the log of number of states of the other system minus the log of the state of the two combined systems. Now, this notion of information is the one that plays a role here, because when two systems interact, in that sense, they get information about one another, right? You can say if a particle hits a screen and then there is a dot in the screen, the dot in the screen it's correlated to the position of the particle. So at the basic level, what happens in interactions is that there's if there wasn't any correlation before, there's correlation after. So there's information which is created, and in this sense, you can derive quantum mechanics. That's the main point about information and quantum mechanics interpretation. you can formulate the core of quantum mechanics in terms of two postulates, plus, if you want, some more technical ones, but two main postulates, which are these two. First, the amount of available information about a finite system is finite. Finite system means, a system with classically has a finite phase space with finite Liouville volume. Or if you want any arbitrary system you want, but you take a finite Liouville measure region. And second, it's always possible to gather new relevant information for any system. Now here, the subtlety is irrelevant. So what is a relevant information? If one system has information about another, because of the equation of motion, I can use the information to predict what the other one is going to do, right? So in this sense, there's relevant information relevant for predicting the future. Some information is not relevant. If I measure 5 times the same thing, I'm not getting new information. I have the information that was measured 5 times, but doesn't tell me more about the prediction of the future. So the minimal I had in the previous slides, the relevant information is the minimum amount of information which is sufficient to give all maximal information that I can about the future. And now this is clear. When I get new relevant information, I always can, since the information is finite, I lose previous information, right? I measure position, then I measure momentum. I have some information about the particle, but I lose information about the position. I measure Lx, I lose information about Ly. And the total maximum amount of information is always the spin. If you think about a qubit, it has 1 bit of information maximal possible, but nevertheless, I can keep measuring every time I get something new. Some new information which become relevant, killing the previous information. Now, what's spectacular, and I don't have time to go through, and I don't want to go into technicalities, you just take these two postulates and you almost completely can get out from that the Hilbert space, self-adjoint operators, unity evolution formalism entirely, with just some additional technical things. And there's been a large literature on that. The best state of the art is in this work by Philip Hearn and collaborators of a few years ago. I'll skip about discreteness because I don't have time. I probably skip about that as well, unless you ask, because I want to use my last few minutes to talk about the wave function. The entire message here is forget the wave function, right? That's really the main message. The wave function is misleading. Schrodinger has misled everybody. Now, the great argument by Schrodinger and by all the people that like the wave function is, come on, the wave function is just a picture of what is going on. But careful, because pictures are misleading. This is a picture of the caloric, right? The pictures of the Ptolemy epicycles, which are extremely convincing when you look them at pictures. But that doesn't mean that the caloric fluid, the phlogisto, is the best way of viewing what happens in heat phenomenon, even if you have a picture of them. So the pictures of the wave function that these are the orbitals of the, doesn't mean that the wave function necessarily is the correct way of thinking of that. And the person who said it more clearly is Schrodinger himself, who was the inventor of the wave function, who went away completely from the idea. I mean, he was first the defender that, okay, this is a reality, is this function there? And later he writes, the inventors of wave mechanics, namely him, Wells, indulged for some times in the fond hope that they had paved the way to a return to a classical continuous description. That's what some sounders would like to do. But again, hope was deceptive. Nature herself seemed to reject continuity description. The gap eliminated from the wave picture have withdrawn to the connection between the wave picture and the observable fact. To the wave picture, the quantum state, to the observable fact, it's a long, complicated story that you can try hard to reconstruct. I don't think it's a convincing or useful story. And then Schrodinger says it's better to regard a particle not as a wave, not as a permanent entity, but just an instantaneous series of events. I'll skip De Finetti, who says basically, forget taking probability seriously. Well, actually, I read it. abandoning superficial credences on the reality of the caloric fluid, the cosmic ether, absolute space and time, theories and witnesses, has been a gap along the construction of scientific thinking. Probability, considered as something exterior, and the wave function is probability, okay? Considering it having a sort of objective existence is no less deceiving and illusory than attempt to put our probabilistic credences outside ourself. So, so what is a wave function? Well, it's just what it is, its classical limit. In the classical limit, the wave function is the exponential of the Hamilton-Jacobi equation. So what is a wave function? Is exactly what the Hamilton-Jacobi function is in classical mechanics, namely a tool for calculating things, certainly not the thing in itself. So this is the main message. If you want to make sense of quantum theory, stop thinking of the wave function or the quantum state as the real thing. Let me skip this because I want to go straight to my final slide, which is once again the overall list of the various interpretation. And here I've sort of you see why I've organized in this way, because the Copenhagen view and cubism go in the direction of a radical instrumentalism. It's a Bohr direction, if you want, right? It's quantum mechanics is not about nature, it's about what we can say about nature. It's about our knowledge about nature. And of course, there's a strong line of thinking against that. Einstein, realism, champion of that, says, no, come on, we want to talk about the reality, not about our pictures about reality. But then there's a lot of cost to add it. Imagine copies of yourself, hidden variables, phenomena that you haven't seen it. In relation to quantum mechanics, it tries a balance between the two. Namely, there's nothing in addition to what we see, okay? But this is not about phenomena with respect to something special, just phenomena of system with respect to other systems, because that's what nature is about. So it's sort of a way of avoiding the two dangers of Scylla and Charybdis, an extreme instrumental in one hand and a overemphasize the ontology because you want to be realistic on the other hand, with the difficulty of going back to what we actually observe. All right, so I've taken more time than what I wanted. This is just references. A lot of that is in the book, which and much more, in fact, in the book that you mentioned at the beginning, Helgoland, which is about the interpretation of quantum mechanics, sort of a popular account of relation of the problem of quantum mechanics and the relation interpretation of quantum mechanics. These are basic old reference. This is philosophers talking about relation quantum mechanics. Many philosophers like it from different perspectives. This is a reconstruction theorem, this is experiments, and this is the book. Thank you very much. And now, sorry for going long. I'm happy to take questions as much as you want.
Thank you so much for this thought-provoking session. So I'll start with a historical question. What motivated the introduction of the non-commutativity equation in the Heisenberg paper?
Yeah, it's a great question. I think the answer is desperation. They had tried everything and the opposite of everything. The actual situation was that there was the old Bohr theory that worked pretty well, of course, but it was obviously incomplete. It gave wrong answer. It did not give the amplitude, and it was a patchwork of strange things. So, and everybody was trying. So the simple picture is this: it was sort of clear that the electron go around the atom, but jumped from one orbit to the other, and there were special orbits, right? That was the Niels Bohr picture. But how could they jump? Think in terms of classical physics. Why those orbits and not other? Why they jump? So everybody was trying to write dynamical equations, change the dynamics so that there's some extra force that make it jump or make it stay on these orbits. So it was always about, this is reality, this is a particle, this is its variable, and nothing worked. Nothing worked, nothing worked, nothing worked. No, nobody was able to doing helium, nobody was able to compute the amplitudes and so on and so forth. in front of the desperation, Heisenberg goes back to Einstein observability. It's just purely a philosophical move. He thinks maybe we're asking the wrong questions, not how the electron moves. He was under the influence of Mach. Mach was saying, you don't understand reality if you put your metaphysical assumptions of what matter is supposed to be. The only thing you really know are the phenomena. So Heisenberg says, all right, in front of this fact that nothing works, let's step back and just get back to the phenomena. Not the atom itself, but the phenomena is what I observe of the atom. That's what he explains at the beginning of his paper. So he, since we observe the jumps, I say I take the jumps as such. So I make a table where in the rows of the orbit from which I'm jumping and the column of the orbit to which I'm jumping. So I have the table of all the possible jumps, okay, because that's what I observe. And then I have a table for the position during the jump, the velocity to the jump, the energy during the jump. So I have a table. And then I have a table of positions, a table of velocity, a table of, okay. All right, so what I've done, I've just rephrased in terms of tables of possibilities of what I observe. And then he says, okay, now let me use the same equations as before. The Coulomb force, the kinetic energy, the momentum is whatever it has to be, okay? And bingo, he gets the correct orbits. And applied to the atoms, he gets the Schrodinger, Pauli, his friend, gets the correct spectrum and the correct amplitudes, which nobody was able to, so the intensity of the spectral lines. So the idea is we are not succeeding. Let's not ask that question. What happens inside? Let's just step up to observability, motivated by a philosophical thing. Remember that all these guys, I mean, Dirac, Jordan, Pauli, Heisenberg, were in the early 20s. I don't know what the age of people in the audience here, but you know, that's the moment of doing great physics, when you're creative and radical. The only old guy was Max Born, who was in early 40s, so 25 years younger than me.
I think it was Max Born who correctly interpreted the tables as matrix mechanics.
Yeah, it was Max Born. In fact, Heisenberg did not know about matrices and matrix multiplication. He just labeled quantities with little indices. And in fact, if you look, the paper is very confusing. I mean, it doesn't have 2 indices or 3 indices to make things less clear. But the idea was there. So much the idea was there that on the basis of his paper, Born and Jordan do the matrix mechanics, and Dirac independently does Dirac quantization with non-commutative variable, which is the same thing mathematically. Now we know the same thing. So it's really the same theory, just on the basis of that paper by Heisenberg. So he had no idea what he was doing, but and he says so. And he comes back for this island. He writes to Pauli. He writes, nothing is clear. Nothing is very clear, but seems that the electron is not going to have a trajectory anymore. So right, he realized that it's a deep change of what we mean by reality, much more radical than Schrodinger wave, but that's the right one, in my opinion.
Yeah, I have 2 more questions about the history. As far as I know, the first paper by Heisenberg was actually written before he went to Helgoland. His visit to the Helgoland was supposed to be a vacation. Is it right? No,
that's not what he says. What he says in his memories, he gives a detailed account of what happened on June 7th, in which so the story he gives is the following. He had this idea of using what we would call matrices today. So the tables with orbits as labeling columns and rows. And he was trying to use that for the atom. but the calculation is infinitely complicated. I mean, it's just it took the genius of Pauli, and after the thing was put in order by Bohr and Jordan. So he failed, and so he tried with the harmonic oscillator with a correction term, which is anharmonic. So it's a one-dimensional rather than three-dimensional system, and it's a much more easy potential. And he tries to compute essentially today, in modern terms, to diagonalize the Hamiltonian, to compute the energy values. So he's in the energy basis already because he used the orbits as, and he has the position and the velocity, everything written in the energy basis, the formulas. And then he has the Hamiltonian, and then he looks at what is the value of the Hamiltonian, and he finds that is 0. And on the diagonal, he finds the orbits which were predicted. He knew what they were because he had the Bohr orbits, the Bohr quantization rules. So he derived the Bohr quantization rules. He finds the correct energies from this funny calculus. And he says that he's doing this calculation on June 7, and it's marvelous. And it starts coming out right because he does it perturbatively. And the first term comes out right, the second term comes out right. And then he gets excited. And then he starts making mistakes. It's June 7. And so he's more excited, so he makes more mistakes. And then he ends up finishing the calculation for this one-dimensional system and finding the right spectrum for the Hamiltonian in modern terms at 3 o'clock in the night on the island. So at 3 o'clock of the night, it comes out right. So he believes it. He says, this is it. I found the new quantum mechanics. He closes everything. He goes out in the night. He climbs a rock and goes up a rock. There's this incredible rocks on the island, and waits for the sunshine, the sun coming up on the rock, looking at the ocean, feeling ecstatic that he has seen something that nobody else has seen before. It's quite moving reading him.
Yes, indeed. Another question about history. Given that, according to you, quantum mechanics was complete in 1925,
yeah.
As what motivated Schrodinger to come up with his equation? Was it desperation to have an understanding of quantum theory, in a classical sense, or was it something else?
I try to see whether in 26, when Schrodinger did the Schrodinger equation, he was in Switzerland hiding with a secret girlfriend in the mountains when he came out with the equation. So it's funny. Quantum mechanics was not born in a laboratory or in a theoretical physics department. Was born in an island in the Northern Sea and in a chalet in Switzerland with this Schrodinger with a lover. The name of the girl or the woman has remained secret. Nobody knows who. Still today, nobody knows who she was. But I've tried to figure out whether he had the papers by Bohr, Jordan, and Heisenberg. I don't think so, because he does not quote them. He does not cite them, and Schrodinger doesn't seem to me the kind of person who would hide the citation like that if the spectrum of the hydrogen atom had been computed already. And the spectrum of hydrogen atom was computed by Pauli in 25 and sent to a journal last days of 25, early days 26, if I remember correctly. And so Schrodinger did not know about that. So the reason he was doing that is he thought that the problem was still open. And he was on a different piste, I mean, a different track. Somebody, I mean, perhaps Einstein, perhaps the historicalists, had given him the thesis of de Broglie. So he was inspired by the thesis of de Broglie, namely that the particles are waves. I mean, Einstein had this idea that waves are particles because the photon. So it comes out to be natural to say, well, maybe also particles are waves. So particle are waves, and then he was thinking, well, if they're waves. So the story goes that he gave a talk mentioning de Broglie ideas in Switzerland, and somebody in the audience asked, okay, if it is a wave, there should be a wave function. What is a wave function it satisfies if the particle is not free? And Schrodinger said, oh, that's a good question. So when he was up in the mountain with his girlfriend, he figured out the wave function, by perhaps by inverting the Hamilton-Jacobi. So the diagonal approximation gives the diagonal. At least that's a motivation he gives. So there's something deeply in common with Heisenberg, because Schrodinger was under strong philosophical influences as well. He was a lover of Indian philosophy. He was a lover of Vedanta, the world as a representation of Schopenhauer, which, by the way, was a philosopher that Einstein loved as well, Schopenhauer. The world as will and representation. So do not confuse the representation with the reality. I mean, he was deeply philosophically influenced, Schrodinger. So unlikely many other physicists of the time, he had no problem whatsoever to think that everything is waves, right? He was a little bit of a hippie kind of guy, him. First, because he was having sex with everybody and his sisters and brother, but also because of his worldview. So he thought everything in terms of his vibrations. But he was a very deep thinker, and Heisenberg and Schrodinger started fighting very soon, publicly, because Schrodinger came out saying, "Look, the wave is a correct visualization. It makes it tells you what is really happening there." Okay, it is. We've found out. I mean, the atom has a little wave going around. It's just, there's a field of waves. It's like electromagnetic waves. And Heisenberg immediately said, "Oh, come on, this is wrong. It's just not like that. Just think, you have two particles, you don't have a wave. You have something in configuration space, a funny thing." And Schrodinger first tried to react. He was wrong. And then later he gave up completely. But matrix mechanics at the time, linear algebra was not taught in Europe until after the war. So nobody knew linear algebra, nobody knew matrices, and in fact, computing with matrices is complicated. You have to be as smart as Pauli to do the hydrogen atom with matrices. While differential equations were something that physicists have been doing for a century. So everybody jumped onto wave mechanics because it's visualizable, because it's easy, because you have all these fantastic tools of differential equations, which so much have been developed. But conceptually, I think was completely wrong. And Schrodinger realized that. So it just focused the idea, okay, we got it. It is a wave. And I think a lot of people, including philosophers in the Oxford department, are still on this wrong path. And look, take Roger Penrose. Roger Penrose has a way of putting the problem, saying, we don't see superposition of macroscopic objects. So therefore, there should be, he says, quantum gravity, perhaps, collapse of the wave function, because the wave function spread, it should concentrate. But quantum mechanics doesn't tell you that you see superposition. Quantum mechanics, textbook quantum mechanics, tells you don't see superposition. You see eigenvalues, right? So when Roger Penrose says, oh, there's a problem, you don't see superposition, he's misreading what is written in the quantum mechanics textbook. Quantum mechanics textbooks don't say there is a wave function. They say, with the wave function, you can compute the probability of what you're going to see. So, moral of the story, forget the wave function, and you get more clarity about quantum.
Right. So the next question is about.
Sorry, I had an interference in my computer, but it's gone. Yeah.
Can you still hear me?
Yeah, it's fine.
Okay. So is there what motivates the two postulates that you mentioned? I mean, is there good reason to believe that these are the right postulates to start? Because there are obviously other reformulations of quantum theory as well. So what makes you think that these are the right postulates?
Good, very good. So I think that, thank you for this question. I think that the way to think about postulates in this framework is not because we need postulate in the sense of mathematical rigor. It's not like the postulate of Euclidean geometry that allows you to. Is it the sense of special relativity, right? Special relativity, you can forget about the postulates. You can just, write the equations invariance and Lorentz. You can start from the Lorentz transformation. You can start from Minkowski space-time. You can start from all sorts of view. But what Einstein did in the 1905 paper is very nice, because he, instead of this strange, hard to read Lorentz transformation, Minkowski space-time didn't exist yet. He came out with two simple statements about nature. Constantly of velocity of light, it doesn't depend on the reference system, and invariance under change of reference frame, and was able to show that from that you can derive the Lorentz transformation. So the Lorentz transformation were already written by Poincaré, by Lorentz, but they were mysterious. Nobody understood what is d prime in this transformation, right? T is clear, X is prime, X prime is clear. It's just a position with respect to a moving thing. This is d prime. And Einstein found the right way of thinking about that with these two postulates. So he said, if you believe that nature satisfies these two things, look, the Lorentz equation come out. So in quantum mechanics, we have this funny formalism, right? Whatever formulation of quantum mechanics is always funny. Take the standard one: Hilbert space, a self-adjoint operator, eigenstates, eigenvalues. I mean, why? I mean, why nature is described as this funny mathematics?
It works.
So my idea was, is there a way of writing down some simple statement about nature from which the Hilbert space eigenvalues, eigenvector formalism derive? Not for playing game with math, which is not my thing, but for understanding what are they hiding. So I'm not saying that these are the best possible postulates of quantum mechanics. I'm sure there are I'm sure there are others, but these are comprehensible. They capture the core we have understood. The first one capture discreteness, because it follows immediately that if you have a finite region of space-time and you want to distinguish, there's a finite number of information to come out. So there's only a finite number of eigenvalues that you can have. So discreteness come out from the first, but it's not discrete in the classical sense. It's the second one is like it captures the Heisenberg uncertainty principle, if you want. I mean, from the second one, it follows as this probability. The second one together with the first follows as this probability. So it's a way of saying, look, this is what quantum mechanics is telling us. There is discreteness. H bar is the measure of the size of this discreteness. And there is probability. So this discreteness, this funny quantum discreteness, right? Quantization of Lx, quantization of Ly are related in this funny probabilistic way. So it's definitely not classical discreteness, it's something else. And I find that all the interpretation of all the other interpretation of quantum mechanics miss the core point of our quantum mechanics, which is discreteness, quantum, right? EH is discrete, a finite way, discrete photons, discrete orbits, discrete element, discrete eigenvalues. So quantum field theory is quantum particles are discrete excitations. So unless you put discreteness as the core, we're not going to understand quantum mechanics. Quantum mechanics is that you cannot zoom, you cannot have infinite information about the system. Classical phase space assume you can zoom down arbitrarily small, so you have an infinite amount of information in any system. Quantum mechanics tell you no. You zoom down, you have a qubit. You cannot go smaller than that.
Right. So you mentioned information in both of the postulates, but as you said in your talk, there are different ways to describe information. So does it imply that information is in a certain sense something fundamental, something physical, which should be part of maybe quantum gravity or the speculative theories of our time?
Great question. I've changed my mind since the 90s about this question, and perhaps more than once. Information was such a natural language for doing all that. In fact, the 96 papers on that, the second half of the paper is entirely in terms of information. I actually sketched the reconstruction theorem. I have the finite alternative, and then the new finite alternatives, and then how to map it in, and then probability comes out. It's all in terms of information that the system has about another information. So I thought, well, that's the right way of thinking about the world. The information system is about another information. And of course, there is a lot of speculations out there about information being the main quantity in terms to think about reality. I've backed up from that at least a bit, because information is always information about something. So we have variables. We describe the world with variables. And the description of the world is systems and variables that describe the systems. And quantum mechanics tell us, in the relational perspective, that these variables are not attached to the system, but always attached to systems in interaction. But we always talk about systems and variables. And we can code the amount of information that system have. So then, or if you want, from a third system perspective, how much two systems can be correlated by measuring it in terms of information. But it's not an information, it's a fundamental thing. It's like in special relativity, is not that, if you want, you don't have to say that the velocity of light is a fundamental thing, or that the invariance under change of reference frame is a fundamental thing. You have theories, classical theories. Electromagnetism is a quintessential one. Standard model is also similar, or locally general relativity, which happens to be such that there is local Lorentz invariance. So locally there is a maximum, there's a light constructor, there's a maximum velocity, and but if you want, you can do all special relativistic physics without referring to the postulates, right? You just forget about the postulates, you just describe Lagrangian with some variables. So I think it's the same thing here. Information is super useful, but it's not strictly necessary for talking about reality. It's a great way of condensing some information we have about how nature works. But I don't think it makes sense to do a foundational theory about information. I used to think more of that in the 90s. I have a little bit abandoned this, this idea. I don't know if I've been clear here.
Right, but information is also there in thermodynamic theories, and
yeah,
you know.
Yeah, I know. It's a look. There was. Let me just add one thing. I think a good analogy is energy. We have a very good understanding of what energy is today. You know, it's related to time translation invariance. It's related to dynamics. We understand the relation between Hamiltonian and time translation invariant and energy. It's a beautiful story. But in it took some time to clarify that story. And in the 19th century, at the end of the 19th century, in the early 20th century, when people abandoned this idea of just particle bouncing around because there were the electric field, the magnetic field that didn't fit in this picture. So people were confused about the foundations. There was a huge movement in physics that said, look, energy is so fundamental that reality is energy. Okay, energy is the fundamental concept in terms of which the rest of the things are, and you still find this around in some. People abandon that, and correctly so. Energy is not the fundamental thing. It's an extremely useful tool, which we understand when it becomes useful. In general relativity, is not so useful. One has to be very careful because in general relativity, for instance, the total energy is just not well-defined thing unless you're in specific cases. If you focus in general relativity that everything is energy, you just get confused. So I think information is a fantastic, useful tool, which we should use every time that there are two systems interacting and one knowing about the other one, because there's a correlation. We can quantify this relative knowledge which is correlation, in bits. Great idea. But I'm not sure we should overdo it and say, okay, the world is information. Yeah, I mean, the world is information, the world is colors, the world is energy, the world is matter, the world is hope, the world is God, but that leaves the time that it takes.
All right, thank you so much, Carlo. I'm afraid we have to end this session, but it was very nice to have you speak and to ask you these questions. I hope to have another session with you maybe in next term. Thank you very
Wonderful.
much for joining us.
Wonderful. Thank you for the opportunity. It was a pleasure.
Bye, everyone.
Bye-bye.